All right, this is a lecture on uncertainty and design of experiments. So remember from last time we started with estimating this utility model, which we write as beta primed x. This is our observable utility, and this error term with the unobservable. And this beta prime x is really just a matrix notation of writing out this same thing here, a sum product of different beta coefficients and the x attributes. And we want to understand what are these beta coefficients. So we estimate this using maximum likelihood estimation, which we rewrote here in negative null form as minimizing the negative log likelihood. And this whole process results in point estimates of our beta vector. So we get an estimate, that's what this little hat here means, an estimate of the vector of beta parameters. But these are not precisely known. So in this lecture, we're going to start figuring out how we can estimate the error around these point estimates. So a general concept to keep in mind is that the certainty of this beta vector is inversely related to the curvature of the log likelihood function. Okay, what does all this mean? Well, let's look at the comparison between this plot on the left and the plot on the right. On the left, the variation here in the log likelihood term is pretty wide, right? We have a very large variance, and on the right, it's much more narrow. So conceptually, if you move away from this parameter beta by just a little bit to the right or left, well, you're not going to get much change in the log likelihood. Just think about when we go from this line here to this line, the log likelihood only drops a tiny bit. And so you could be over here or you could be over here, and any of these points of beta could still produce the same log likelihood. Over on the right plot, that's not the case. As soon as you move away from this line here where the best estimate of beta is, well, you very quickly reduce the likelihood. And so the difference here is on the left, when you have a much greater variance in the log likelihood, well, that means you're less certain about beta. And the opposite is true on the right. You have a very narrow band around the best estimate of beta. And so you have very little variance in the likelihood function, which means you are much more certain about this beta coefficients. So there's an inverse relationship between the coefficient beta and the curvature of the log likelihood function. And remember, the curvature of a function is related to its second derivative. So in this case, the covariance of this beta term is related to the Hessian of the log likelihood function. Remember, the Hessian is the matrix of second derivatives. So this inner term inside this bracket is just this Hessian matrix that comes out of our estimation procedure, and then we take the negative inverse of it to get our covariance. And so this results in a matrix of lots of variance terms. So visually, let's just imagine we only have two betas, beta 1 and beta 2. Well, these sigma terms are going to describe the size of these rings. If we're looking down at an overhead plot of this is kind of like looking at like a topographical map, where our best estimate of our vector beta is this point here, beta 1 and beta 2. But the true parameters could be somewhere else in this space. And the broader this space is, the less certain we are that this point is the optimal point. Oftentimes when we report our results, we'll just report the sigma terms that come off the diagonal of this covariance matrix. So you'll see tables like this where you have your estimates of your different coefficients for beta, and there's standard error, which is the square root of each of these terms along the diagonal. We'll use these terms to report uncertainty about beta. So imagine that each of these beta terms is really a distribution of possible terms for beta. And beta hat is just the mean of this distribution. This is our best guess of what the true beta is. If we add one sigma to either side of this beta term, well, that captures 68% of this distribution of possible betas. And if we add another sigma term on either side, that captures 95% of this probability of possible different betas. As a convention, we usually present 95% confidence intervals as approximations where we take beta hat and we subtract 2 sigmas to the left and 2 sigmas to the right. So these bands here on the outer edges would give us a 95% confidence interval about what the true parameter of beta is. So for practice question 1, let's say we estimated a model. Our beta coefficients are beta 1 is negative 0.4, beta 2 is 0.5, and this is the Hessian matrix, the matrix of second derivatives that result from our estimation. Part A, use the Hessian to compute the standard errors for beta hat. And part B, use the standard errors to compute a 95% confidence interval around beta hat. For some hints, the covariance matrix, remember, is computed as the negative inverse of the Hessian. And in R, you can compute this by first using the matrix function to construct a matrix in R, and then use the solve function to compute the inverse of a matrix. And finally, you can use the diag function to get the numbers along the diagonal of a matrix. The uncertainty around our beta coefficients is also related to how we design our experiments. Because we're using surveys, we can control what information we're going to get about each different attribute we're interested in. For example, let's consider that we are interested in 3 main effects: an effect A, an effect B, and an effect C. This cube represents the full design space of these effects being positive or negative. At the origin, all 3 effects are negative. This corner represents the effect where A is positive but B and C are negative. This corner represents when B is positive but A and C are negative. And this corner represents when C is positive but A and B are negative. We also have the two-way interaction terms between AB, BC, and AC. And finally, the corner where all effects are positive. We're typically interested in main effects, or the average change in the dependent variable that's associated with a change in one attribute level. So for example, the main effect for A is going from the side where A is negative to the side where A is positive. If we had observations from every one of the corners in this design space, then we would compute the main effect as the average of the positive A side, so that's the average of these 4 corners, minus the side where A is negative, so that's the average of these 4 corners. An interaction effect measures the difference in the main effect of one attribute based on the value of another. So, for example, if we wanted to measure the interaction between A and B effects, then we would compute the effect of going from when A is 0 to A is positive on the side where B is positive, and we would subtract that from going from A is negative to positive where B is negative. So to compute that, we would take the positive A effect minus the negative A effect when B is positive, and we would subtract off the positive A effect from the negative A effect where B is negative. If we have observations on every corner in the design space, we call this a full factorial design. In this case, each of these rows would represent a question in our survey, and if we had an observation about each one, we'd be able to measure any effect in this whole design space. Now, full factorial designs have several properties. One of them is that they're balanced. This means that for each attribute, all levels appear an equal number of times. So let's just look at the A attribute. If we count the times where A is positive and negative, we'll see that it's equal. There's 4 negatives and 4 positives. The same is true for B. We have 4 negatives and 4 positives, and C, 4 negatives and 4 positives. So this is a balanced design. It's also orthogonal. Orthogonal means for each pair of attributes, all pairs of levels appear together an equal number of times. So let's look at the combination of just A and B. In this case, A and B are the same 4 times. Here they're both negative, here they're both negative, and then they're both positive here and here. They're also opposites 4 times. Positive, negative, positive, negative, positive, negative, positive, negative. So there's an equal times that they're the same and opposite. The same is true if we look at B and C. They're the same 4 times and they're opposite 4 times. And the same is also true for A and C. So when we look at the combination of different attributes, when we find that their pairs are equal numbers, then that's an orthogonal design. Now in this case, because we only have 3 effects and each of them only take the values of positive or negative, we only have 9 possible effects we would want to measure. But as the number of different effects we want to measure grow, a full factorial design may not be feasible. We simply may not be able to ask about every possible combination in the design space. And in that case, we often rely on fractional factorial designs, which are just a subset of the full factorial. So let's look at this particular subset. This fractional factorial design is balanced because for each attribute, there's an even number of times where the effects are positive and negative. 2 negatives and 2 positives for A, the same for B, and the same for C. However, it's not orthogonal. If we look at the effect of A and B, we see that there's 4 times where they're the same and 0 times where they're the opposite. So this is not an orthogonal design. In this case, we would say the main effects of A and B are confounded, which means we can't separate these two things apart. We can't be sure if a consumer likes attribute A or if they like attribute B, since they co-vary together. If we calculate the main effects for A and B, we'll see that they're exactly the same. The side where A is positive is these two terms, and we would subtract away the side where A is negative, which is these two terms. Well, it's the same for B. These two terms are the only ones available for when B is positive, and likewise these are the only two where B is negative. Every fractional factorial design has confounded effects, and we can find the other confounded effects by doing a simple trick. If we know that A and B are confounded, well, we can just multiply the other effects by this A equals B. So if we multiply the C effect with A and B, we get that C times A equals C times B. And so the effects for BC and AC are confounded. When you multiply B times A equals B, you get AB. And when you have two terms that are the same, B times B in this case, those cancel and you get I. When you multiply AC times A equals B, the A's cancel and you get C equals ABC. So the ABC term is confounded with the C term. Here's a different fractional factorial design where we have A, B, and C and the term ABC. In this case, they're both balanced and orthogonal. If we look at the combination of different attributes, we see that they are opposite the same number of times that they're equal. So look at A and B, we see that A and B are the same for these bottom two rows, and they're opposites for the top two rows. The same is true for B and C and the combination A and C. So that's an orthogonal design. Now, in an orthogonal design, none of the main effects are confounded, which is often a good thing and usually what we're mostly interested in. But keep in mind that because it's a fractional factorial design, there are other confounded effects. In orthogonal designs, the main effect is confounded with a two-way interaction. The A term is confounded with BC, the B term is confounded with AC, and the C term is confounded with AB. Finally, the ABC term is confounded with the I term. So in general, if you're only interested in main effects, an orthogonal design could be an efficient choice for your design. But if you're interested in interaction effects, it may leave you unable to explain certain interactions. When you're designing your experiment, consider the following different questions. First, can you use the full factorial design? If you don't have too many attributes and each of those attributes don't have too many levels, then you may be able to use the full factorial design. In making this decision, you also have to consider what your sample size is likely to be and how many questions each person is going to answer. If you decide that the full factorial is going to be too large, then you have to ask yourself, can you ignore the interaction terms? If you're only interested in main effects and you don't expect to have any important interaction terms, then consider using an orthogonal or a main effects design. This will give you more information about each main effect while confounding the interaction terms. But if you think there might be important interactions, then you might just want to consider using a randomized design. In a randomized design, you just randomly select different rows from the full factorial design. So for practice question 2, consider the following experiment design. We have these 4 rows with the effects A, B, AC, and BC. A, is this design balanced? And is it orthogonal? And part B, write out the equation to compute the main effects for A, B, and C. Finally, are any of the main effects confounded? If so, what are they confounded with?